In these sections, we have miscellaneous topics. Basically, here there's a two. One is bulk modulus. One is the relation between the three quantities, three material properties here. The first one, we look at what is the bulk modulus and what it is for. Basically, that bulk modulus is related to the dilatations. Dilatation is a concept like this. You assume that it's a deformable object, and this object is immersed in the very deep water, and such that it's under uniform pressures from all the directions. Okay, so pressure compressive to compress. And assuming you can imagine due to high pressure, the volume going to change, and actually the volume change is going to be small. Okay, so here we have involved two quantities. One is the magnitude of the pressure this object is experiencing. The second quantity is about the change in volume. Basically, delta V over V is called the relative the volume change, and actually we have a simple name, simply called the dilatation, defined by E. So here the bulk modulus is simply related to the quantity ratio P over E. And here why we add a minus sign here, because you can imagine the whole volume change is become smaller, so in reality E will be say negative. Okay, so basically the whole quantity P over E in nature is negative, so we artificially assign a negative sign here to make the whole quantity positive. So basically here again, this negative sign is to simply make this whole calculation as positive as defined as the bulk modulus here. So again, here we involve the calculations of two quantities, and in particular is this one. So this page we dedicated to how to calculate the dilatation, and by definition we start from here, from definition of this. So delta V equal to the change in volume, and that basically here is defined with deformed minus undeformed one. Okay, so we measure the deformed volume and then compare it to the undeformed one, we find the difference. So deformed volume can be estimated by this. We assuming these objects have the length L, width W, and height H in X, Y, Z directions. So then under the deformation, we know there's a corresponding strain. So in strain in X. So this one basically telling is the deformation in X direction. That deformation is caused due to the pressure, the application of the pressure. So this is deformation. Deformation plus original length. This whole quantity represent is the dimensions in X, and the X dimension in the deformed object. Similar way, this represent the Y dimensions in the deformed object. Okay, and that is the dimension in the deformed object. So here I turned L, W, H out, so basically simply become this. And on deformed volumes, very simple, is original shape, simply is a multiplication of three dimensions here. So we put the two terms into this definition here, then we can simply do the calculations, and so basically become like this. Okay, and the multiplication of the three terms simply can be further expanded into three and then higher order terms of the multiplication of the epsilon x, epsilon y, and epsilon x, epsilon z, etc. Okay. So that is the original expressions, and now here let us make assumptions. And in elasticity, and probably from the exercise you have done before, you know the strain can be very small. So we assume that is a small strength and small deformation. So basically the multiplication of the small numbers will become even smaller. So here we can ignore, we can approximate the higher order terms become 0. So the whole dilatation basically is simply pick the linear term here. Okay, so here we simply approximate the higher order term equal to 0. And then from here, that is become very clear. And here it simply is the summation of the three normal strings. And we remember we have Hooke's law and relating the strain to stress like this. So simply in the next step, I simply introduce the normal strength by the three terms here to relate it to the stress. Okay. So after the arrangement, we have this one here. This one basically relating to the dilatations, and then also remember the stress in XYZ direction simply is the uniform pressures. Okay, so magnitude is P of the pressure and put the minus sign indicating that it's compressive. So plugging here everything here, E equal to this one, then we rearrange and put into the definition bulk modulus and basically equal to this. Okay. So this is a very simple applications of what we have learned, and this slide basically is the explanations from our textbook, and you can exercise the same reasoning, but that is the same exactly what I did here. One thing I want to mention that the dilatations must be the dilatation E. This value E must be negative, so that implying the Poisson ratio must be in this range. And even I can tell you in all the natural materials, the Poisson ratio is confined in this limit. So basically, for all the natural materials we should expect the positive bulk modulus. The second topic is in this section is about the relation between the Young's modulus, Poisson ratio, and rigidity modulus. By ignoring the little bit detailed explanations, I don't think that's critical here for the beginners. We simply pick up this one. Okay, so this relation simply saying that as long as you have any two, say if you have E and G, then you should be able to calculate nu Poisson ratio, and vice versa. If you have the Young's modulus and Poisson ratio, then you should be able to estimate the G, okay, by this formula. So given any two of the three material properties, the other one is derived. Okay, so that is the section.